Okay, so we're going to be talking about the beginnings of the chemical evidence, so trace evidence in forensics. And so a lot of times when we get these crummy, crappy samples out of someone's trunk or stuffed in their shoe or carried in their gut for miles as a mule, I mean, there's lots of things in there that are not analytes. And we may have multiple analytes. And so what we have to do is we have to figure out how to deal with these strange mixtures. And so that's our sample prep. And sometimes you might have a fairly pure powder that you can dilute it, put it in a solvent, shoot it onto the GC or the LC. And that's great. Sometimes the matrix is irrelevant because it's a powder and you can dissolve it in whatever solvent you want. Other times you have a heterogeneous system. You've taken a wipe or a filter and you've got to get the analyte off that surface. Sometimes, like in cellular material, your analytes are trapped inside the cellular matrix, and it's not going to just be accessible to whatever probe you have. So you have to make it homogeneous by mixing it. So you put in an ultrasonic probe or something that destroys the cellular materials and releases the analytes. And then we went over a few lectures ago this lab sample. So I went ahead and put this equation back in here for you. So if you have less than 20 packets that you need to analyze or field samples, you analyze all 20. If it's above 20, then you analyze 10% of those that are above 20. So this sort of two conditions in this to determine how many lab samples you have. So our example was if you have 100, then you would analyze 20 of those, and then that leaves 80, and you'd analyze 10% of that 80, so that's 8. So you would analyze 28 lab samples to characterize 100 packets or 100 bottles or 100 whatevers. Okay. So we've kind of come up, these are pretty obvious what we have here. What's not so obvious is this partitioning, separating the actual chemicals. And so we're going to spend all our time today really talking about chemical separations prior to, say, chromatographic separations. So some of our instruments, like all of the different chromatographies, gas chromatography, liquid chromatography, ion chromatography, those are the big three: gas, liquid, and ion. Okay. We could also have electrophoresis. So capillary electrophoresis is a separation technique. We could have gel permeation or size exclusion chromatography, which is another form of liquid chromatography that could do polymers. But sometimes before we go into those pieces of equipment, we want to separate our analytes and get them apart from each other, especially if they're going to interfere with each other. So this is where we get into chemical partitioning. And I say, let Le Chatelier drive. So we're going to be talking about Le Chatelier's taxi today. And a taxi is a great thing, right? You take it where you want to go. And if you want to go back, you get in it and go back. And so this chemical equilibrium I think of as a taxi. If I want to go to the products, I get in and I drive over to the products. If I want to go to the reactants, I go the other way. And the driver of that taxi is pH. So we tell pH where we want to go. So if we want to go to the products and we have an acid or a base, we can tell the driver we want to go to the products, and the driver will pick the associated pH and get us all the way over there. So this is to separate our analyte from the matrix or from interferences, or analyte number one from other analytes. Okay. And so we can use this equilibrium. We have this generic reaction, chemical reaction, A moles of species A and B moles of species B, etc., making the products C and D. And we have our equilibrium constant. So this is all familiar. Remember that it's the species C raised to the exponent of the number of moles of C, and D raised to the number of moles of D, and so on. So this should be review all of these equilibrium constants, and we're going to be using this quite a lot today and in the problems associated with this work. Okay. Now let's refresh our memory on what K is. K is the equilibrium constant. So it's related to the forward and reverse rates of the various species and how complex the reaction is and so on. And sometimes this reaction lies far to the right, meaning you have way more products than you have reactants. So you look at that KEQ, products are on top. So if it's much greater than 1, then products are dominating. If it's much less than 1, then the reactants are dominating. It doesn't go forward very much at all if it has a small K. Notice the Ks are not negative because we don't ever have negative concentrations. So it's just, really less than 1, which would be your 10 to the minus exponents, and really greater than 1, which would be your 10 to the positive exponents. If it's exactly equal to 1, then your reactants and products are sort of equally matched. Okay, that doesn't mean they're the same concentrations because your powers might be different. You might have some squares and some cubes. So what do we do with this? Well, acid-base solubility and redox equilibria are useful for partitioning your analytes. So we can use this, especially pH and solubility, to really drive our reactants or whatever species we're interested in. Let's say we're interested in C. So we might adjust the pH so that products dominate, and then we get C. If we're interested in B, then we would have to adjust the pH so that reactants dominate. We would drive this reaction backwards and force it to be mostly B. So let's look at pH. Let's give a little survey of pH here. This is from acidic to basic. Here's a bunch of common things that we have here. Household ammonia and certain forms of household bleach. If it's like sodium hypochlorite, then it's a very basic compound because it's been fully deprotonated. Sodium hydroxide is the strongest on this list. So those are the really high pHs, very basic compounds. They are looking for protons. They will deprotonate all your acids, weak or strong. I mean, they are looking for protons because you have all these hydroxides in a basic solution. So as soon as they find a proton, they make water. Okay. The opposite end, you have low pHs like lemon juice, stomach contents. Wine is pretty acidic. Tomatoes are pretty acidic, pH 4. You get into some of the more acidic black coffees, a pH of 5. Okay. And then here in the middle range are like milk and human blood and tears. They're all pretty neutral. That doesn't mean that it's pure. Pure water has a pH of 7, but also things that are buffered can have a pH of 7, and that doesn't mean that it's pure water, right? Okay. So you might have seen emails where it talks about Coke, dissolving meat, like you put a steak in Coke and leave it for 2 days and it totally dissolves the meat. Have you seen any of those? It's got phosphoric acid in it. Oh no. Okay. And here's the emails that were going around. Every once in a while you get one of these. Coke has responded to this, and they're like, we have no evidence that the highway patrol is carrying around Coke so it could dissolve blood from the highway or scenes of crimes. Okay, so this is mostly bogus. They said, plus it would be totally cost prohibitive because vinegar would do the same thing and probably work better. So, you see on these emails, you could put a T-bone steak in a bowl of Coke and it'll be gone in 2 days. You could clean a toilet, pour a can of Coke in a toilet bowl and let the real thing sit for an hour and then flush clean. The acid in the Coke removes the stains. And to remove rust spots from chrome, soak aluminum foil in Coke, and remove corrosion from battery terminals, pour a can of Coke. So it's trying to make you afraid of drinking all these sodas and so on. But what are you doing when you drink a soda? You're taking something that has roughly a pH here, see cola and vinegar, a pH of 3, and you're putting it in your stomach, a pH of 1. Okay, so you're like, oh, there's acid in Coke. Yeah, there's acid in your stomach. If you throw up on a T-bone steak, it'll dissolve it. If you throw up in the toilet bowl and let it sit, it'll clean the stains. It'll be nasty, but that acid will get rid of the stains, okay? And certainly if you throw up on your battery, all that corrosion on those terminals will get eaten away too. It might even eat up some of the lead. So I don't recommend it, but I'm just saying that this email is ridiculous, like trying to scare you away from phosphoric acid. And in fact, your body is buffered with phosphates and with carbonates and so on. So anyway, it's just kind of fun to point that out to people who are like, oh my gosh, Coke has acid in it. Yeah. So does lemon juice. Don't put it in your tea. Okay. All right. So that's our tour of various acids. Now let's refresh our memory too on polyprotic acids. So these are acids that have more than one acidic proton, one that can be donated. And again, our definition of an acid is a proton donor. So an acid, we'll go ahead and say that. And so there's lots of compounds that, well, like take acetic acid. It's got one proton that's donatable. It's a carboxylic acid. The methyl group on the end has 3 hydrogens on it that are more covalently bonded to the carbon. They're not acidic protons. And so even though acetic acid has 4 hydrogens on it, only one of those is a donatable proton. Now, what do we mean by proton? Well, it's an H+, right? And H+ has 1 proton, 1 electron. If it just is an H+ donated to something else, you've just donated a proton to another molecule. And if you donate a proton to something, what are you doing? You're changing its charge, okay? If it's negatively charged and you protonate it, now it's neutral. If it's neutral and you donate a proton, now it's positive. And so whether it's ionized or not is a really important concept. So whenever we talk about ionization today, I want you to turn your ears on for sure. Now, these are polyprotic acids, and you can look at these Kas, and right around where the Ka is, that's going to be its buffer region. And so pKas, so good buffer regions of pH. Hopefully you can read my writing here. So if I'm looking at phosphoric acid, I've got 3 protons here. And so there is a pKa, Ka1, that's going to be roughly between 2 and 3. So what am I doing here? I'm looking at this 10 to the minus 3. And if I take the minus log of that, the log brings down the exponent. So I have a minus 3. And if I take the minus log, I get rid of the minus sign. So I can just look at this 10 to the minus 3. And I could say that's roughly equal to a pH of 3. Did you know you could do that? You just take those exponents, and that's roughly the pH if we take the pKa. And the pKa's in these acid curves, if you were to titrate this acid, it would come along here and do this. So this would be phosphoric acid. Okay. pH and mils of base. And this is going to be pKa1, pKa2, etc. Okay? These flat regions. Now, what is that telling me? If it's flat, I'm still adding base right here. I'm adding a lot of base, but the pH curve is flat. That's what we mean by buffered. So right around where those pKa's are, the pH doesn't change much, even though I'm adding strong base. So that's what we mean by a buffered pH. So wherever the Ka's are, you can look at those, take the minus logs, and that's where that acid will buffer things. Phosphoric acid can also buffer things around pH 8, and then really basic, if it's if you remove all 3 protons, it's a very basic compound, a pH of 10 to the minus 13 or pH of 13. Now, sulfuric acid is a strong acid, so it's 100% ionized for that first proton. So that's why it says large. Okay, but then the second proton comes off at a pH of, pH of about 2 would be its buffer for the second proton on sulfuric acid. So let's review our ice tables. Remember those? All right. Come on. I see a few people groan. Don't write yourself off. You learn something the first time, it's really tough. You don't quite get it. The second time, you're like, okay, I think I got it, but I'm not sure. Third time through it, you're like, okay, now I got this. thing is, let yourself get it. The self-talk is what kills you on these things. You say, I didn't get it the first time, I'll never get it. That's crap. Okay? So anytime you run into a tough topic, you say, oh gosh, I had a hard time. I don't understand that. Put a yet on the end. Can you do that for me? So when you say, I don't understand, I don't understand them yet. Okay? So work on them. And here's one we'll do from scratch. So here's calculate the pH of a 2 molar solution of amphetamine, and they give you the pKa. Now, what do you see in this name, amphetamine? It's a bunch of stuff, amphet, which I have no idea what the heck that is, and amine. That's base. Okay? And then I'm given a pKa, which is just the way we do things. We give you the acid constant, even though it's a base. Okay. I didn't make the rules. Okay. So we first got to write out the reaction. So we're talking about the solution of amphetamine. So we put amphetamine, which I'll just call B for base, in water, and it makes BH plus and hydroxide. Okay. So it takes some protons, since it's a base, it takes a proton from water, it makes hydroxide, and then it's now ionized as a BH plus. Okay. So this is a generic reaction for all bases. Nothing specific to amphetamine. Like pKa is the thing that makes it specific to amphetamine. So we're going to think about this. If we're given the pKa or the Ka, then we can compare that to Kw in order to get the Kb. So the pKw is 14, because this is 10 to the minus 14. And so if we know that the pKa is 9.8, then this right here is going to be, 14 minus 9.8. So we can find the pKb. Okay. So here's our ice table. We have initial conditions, we have a change, and we have equilibrium conditions. And that's what the ICE stands for. We put 2 molar over here as our reactant. We have 0 for the base and 0 for the hydroxide. So we're going to run this reaction forward. We're just taking the nominal concentration from the problem to start with. So that goes in here as our initial condition, and we're going to say how much is left after it comes to equilibrium. Because at this point, we don't have any hydroxide ion concentration, so we don't have any way of calculating the pH. So we have to let it come to equilibrium before we can calculate the pH. And so let's find our Kb. So here's our reaction. It's, again, written in the form of a base. And so our products are on top, BH plus and OH minus, divided by our parent base concentration. And water's not in here because these concentrations are for the aqueous species. So this is, because it's aqueous, we're looking at the concentration of the protonated base in water. Whereas this is liquid water, so it would be the concentration of liquid water in liquid water. That's going to be a constant. And so it's lumped into K. So all of the times you see liquid water or solid substances, those are not going to show up in the equilibrium expression. Only the aqueous species are going to show up in the equilibrium expression. And so that's what we're dealing with. So, but we need Kb. So Kb is Kw divided by Ka. I'm kind of using this one here. This equation. And so that's 10 to the minus 14. And then this, I took the anti-log of 9.8. So 10 to the minus 9.8. So I basically did the pKa thing backwards. And that gives us our Kb. So there's our equilibrium constant, actually. Since we wrote the reaction in terms of a base, we have to use Kb. That's the key. You can't use Ka when you write the reaction as a base. How do I know I'm writing it as a base? Well, this is the base, and it's stealing a proton from water. Bases are proton acceptors. So it's accepting a proton from water and producing hydroxide and becoming protonated. Okay. So now we have our K, we have our initial conditions. How do they change? There's the plus and minus X business, right? Find your double-headed arrow, and that's what divides your ice table. The things on the left of the ice table are negative, so we're losing X's, which are reactants, and we're gaining products. So those are the positive x's. And so then we look at this, we have 2 minus x, and I put approximately equal to 2. That's an assumption. We're going to check that later. But we're going to assume this first, and then we'll calculate it, and then we'll see if x is small. So we'll figure out a rule of thumb for making that assumption, but we could just calculate it, assuming it's not important, and then see if it is. Okay. So here's our expression. We have the two species on top are now x, and so it's x squared. So you see that right there, that became x squared. And then the species on bottom, we're assuming is just 2. So we can solve this pretty easily. We take the 2 over to the other side and take the square root. So we solve for x, which is the concentration of hydroxide ion. And we see 1.123 times 10 to the minus 2. So that's our x value. So we could compare that over here. You know, this little x here is 10 to the minus 2. So yeah, it's really small. I mean, we could maybe be a little more accurate, but that's good enough. We have less than 1% error, okay, making that assumption. But the problem's asking not for the hydroxide ion concentration, it's asking for the pH. So we need the hydronium ion concentration, and then we need to take the minus log of that. So this is our Kw. If we know Kw and we know OH, we're going to be able to get the hydronium ion concentration. If we take the minus log of everything, we have the pKw over here, which is 14, is equal to the pH plus the pOH. And so if we take the minus log of this number, we get the pOH. And then we can just subtract it from 14. So we have the pOH, the minus log of that number. And it's the log log, not the natural log. It's a base 10 log. I'm trying to think of all the places where I've seen people mess up. Okay. And then pH is 14 minus that. So 14 minus that number is 12.05. It's a pretty, it's a basic compound. Put that in water. If you can get it up to 2 molar, if it's that soluble, then you will have a pH of 12.5. So this is our little rule of thumb. What is C base? Well, C base is right here. This is equal to the nominal concentration of base. It came from the problem. And Kb is over here, Kb. So C base is 2, and our Kb is 6.31 times 10 to the minus 5. I don't really need to get my calculator. I know that 2 divided by something at 10 to the minus 5 is going to be greater than 100. So that's a check. So since that checks out, I know I can make this assumption. So that's a nice rule of thumb. That keeps your error under 1%. And so if you just look at how much you've got in solution and you check it by your equilibrium constant, you can make that call. So that's a nice rule that you can put a star by. Okay. Let's make it to where it's not okay. Okay, where that rule fails. Okay. Oh, and then percent ionization, that's a new calculation I like to, I mean, not new, but I'd like you to know. So it's if you look at this, we have the BH plus, and let's say that's what we wanted to detect, or we wanted to use that to drive it into, say, the aqueous phase from an organic phase, because the aqueous phase is going to like ions more than the organic phase. This is only 0.56% ionized. That's not 56, that's 0.56%. See, it's the concentration of BH plus right here is 1.123 times 10 to the minus 2. So it's really small amount of BH plus. So, it's not very ionized. It's less than 1% ionized. And notice how this percent is. It's part over whole. It's the ionization part over the whole. Times 100%. Does that make sense? So whenever we're talking about percent ionized, you have to have part over whole. The part is the ion part. Now for an acid, the ion part is the anion. And it's the deprotonated acid that's ionized, and it's the protonated base that's ionized. So that's something that people really get confused on. But just think about it. What's an ion? It's the charged thing. So it could be negative, it could be positive. Whichever one is, in your species, that's what you're looking for. Okay, so here's an ice table with the quadratic equation. So same question, but with a different concentration, 0.0025 molar. So our little check fails. If I take that and divide by Kb, it's not greater than 100. So I can't make that assumption in my ice table. So here's my ice table. My C base is 0.0025 molar. We have our change, calculation minus x and plus x plus x. And then at equilibrium, I've got to keep that minus x in the denominator for my equilibrium constant expression. So here we have x squared over 0.0025 minus x. So we've got to rearrange this to get it in the standard form for the quadratic equation. So we're multiplying both sides by the denominator, and then we're rearranging and subtracting so we can get 0 on the left and x squared and x and so on. So we have it in that form, ax squared plus bx plus c. So now we can use that quadratic formula that we have memorized. I never learned the song. Did y'all learn the song? There's a song associated with this equation. Since I never learned it, I can't teach it to you. But one time I got to this point and the student started singing this song. I was like, wait, what's going on here? So anyway, if you know the song, you can record yourself and send me the video and I'll play it. Okay, yeah. All right, so then we take all of these pieces and we stick them in the quadratic equation, and it looks pretty ugly. Now, one thing, I don't know if you learned this, but whenever you have a plus minus in the equation, you're going to end up with two results. And so go ahead and put a plus by the one that used the plus and put a minus by the x that used the minus. Does that make sense? So you can keep track of which one is which. And so how do we know which result to use? That's where your thinking comes in. So you look at the results and you say, oh, goodness, one of those is a negative concentration. So that's crazy. You don't want that to happen because you put 0.0025 moles of this stuff in solution and all of a sudden even more shows up somehow. Anyway, that would not be cool. So we don't use the negative concentration in our calculations, we use the positive one. And so that is X, so that's going to be our concentration of OH. That's going to be our concentration of the BH plus. So the POH is the minus log of that. And then the pH is 14 minus the POH. So 10.56. It's less basic, right? The pH is lower than it was. Earlier I had a concentration of 2 molar and it was 12, a pH of 12. Now I have a concentration of much less than that and it's pH of 10. So 2 orders of magnitude drop in concentration because I had less base. Okay. And we can see that minus X was significant. It went from 0.0025 to 0.0021. So yeah, it was, it changed in the first or the second digit. So we couldn't ignore that X without making a substantial amount of error. And then if we take that concentration of 0.0036 and divide by the 0.0025, we get that this is 14% ionized. And that is enough to drive this, more into the aqueous phase. So 14% is not great, but it's better than 0.56%. Okay. Any questions on this sheet? This is the longest one, this quadratic formula one. We'll do one more. And the next one, notice we haven't used the taxi yet. We're just letting things come to equilibrium. Now we're going to drive this reaction forward using acid. Okay, so let's say we want to get all of it ionized because we want to analyze the BH plus. We want to separate it from everything else. So we could dissolve this in an organic solution because it's an organic molecule. It's an organic base, so it's soluble in organic. We get it in organic, we put it in contact with water. Okay, it's not super soluble in water, but if it's ionized, it's very soluble in water. So we put some acid in the water. So whenever one of those basic molecules reaches the interface of water and organic, that gets protonated, and then water sucks it out of the organic phase. So if we could drive this to be all protonated, it would all go into the aqueous phase. And that's fantastic. That's where we're headed. Okay, so let's look at that situation. So this is speciation. You know, these are two different species of amphetamine. There's the neutral amphetamine, and then there's the protonated amphetamine. So those are species. Same molecule, but one's protonated, one's not. And so if BH plus is what we wanted to detect, we want as much of that as possible. So we want to drive this reaction to the right. And one way to do that is to put it in contact with acid. So look, my reaction has changed. Now I've got B plus a hydronium ion gives BH plus water. So we're driving this to the right. We put acid in the reactants. We're going to put it in an acidic solution, and that'll drive it to the right. Now, because we have an acidic solution, okay, we're going to protonate all of this base, except for maybe a tiny amount. Like there's going to be 10 to the minus 10 or so molecules in there per liter that are moles per liter that the acid just can't find, right? So in equilibrium, as acid's trying to find this base, there's going to be a few hiding out in the corner of that solution that the protons just on average can't find. Okay, they might find one, but then another one gets deprotonated. So the forward and reverse reactions are in equilibrium. That's what equilibrium means. So this is the step that confuses everybody in this class. Okay, this next step. If I know it's going to go mostly to the right, like really mostly to the right, I'm going to drive it 100% of the right. So how do I ensure that it's 100% to the right? Okay, here's my double-headed arrow. I'm dividing the table in two here. So I have negatives on the left and positives on the right. And 100% to the right means this goes to 0. Do you see this right here? This goes to 0. That's what I mean by push it all the way to the right. Okay. We'll see why this is in a minute. Okay. We have so much more acid than we have base. That's what's driving it to the right. So if we push all of this to 0, what is x? Right? 0.0025 minus x equals 0. So this right here means that x is equal to 0.0025. So x equals 0.0025. And once you find x for the whole table. So that means this is 0.0025 as well. So I take this acid amount, subtract the 0.0025, and I end up with this number. Does everybody see where this number came from? Once I find x, I can do this subtraction. And once I find x, I can do this addition. I have 0 plus that gives me 0.0025. So I will pause here to make sure if you need clarification on this step, you can ask questions. This is Le Chatelier's taxi. We're driving it all the way to the right, and then we'll do an ice table reaction to see how much it comes back. So it's going all the way to the right, and it will come back just a tiny amount. You can kind of see through the faded parts where we're going to go with this. But yeah, mathematically, we're making it go all the way to the right because we know we have so much acid. It's the acid that's driving it to the right. We've used up all the base and we still have acid left to go. It's like a limiting reactant problem.
So are we determining that based off of the pH?
And so then,
or are we just making it?
Well, because what's funny about this is that pH, let's see, we're just calculating, and the problem here, just calculating the concentration of neutral amphetamine that remains. The pH is going to be stuck at 2 roughly. We'll see. It's not, I mean, it's 0.0075, which is going to be close to 0.01, which will be close to 2. It might end up being like 2.3 or 2.4.
So we're just saying that because it's in an acidic solution,
Yeah.
going to be 0.
Yeah, we can assume 0 and then calculate how much it comes back. Okay. Yeah. And that's what we're doing by putting it in an acid solution. Notice we're adding one of the reactants, and so we're pushing it towards the products. So let's push it all the way to the end and then have it come back just a tiny amount. And we won't need the quadratic formula or anything like that. So now we have this. Notice I'm saying this is a new initial. We did initial, we did 100% change, and then we have a new initial. So this is our ice table here. So this is now a reactant. And these are products. Do you see? Nature hates that zero over on the left. And so that zero is going to go up. There's going to be a plus X over there. And it's going to be correspondingly, since they're on the same side of the reaction, hydronium ion is going to be plus just a tiny amount too. And then there's going to be a minus BH plus. We pushed it all the way to the right, but nature won't go 100%. It's going to come back a little bit. So we pushed it all the way to the right, and we're going to calculate how much it comes back. Now, looking at this reaction, if I run this reaction backwards, that's BH plus water gives B plus hydronium ion. That's the BH plus. That's the acid form. So use Ka. So we're going to let that reaction run backwards. And so here's at equilibrium, we'll have 0.0025 minus X. It's going to be essentially unchanged. And the acid plus X is essentially going to be unchanged. And so the only thing that's going to change, zero, anything added to zero is going to be significant. And so we have X here. So this is a very simple equation. It's just got one X, no X squared, no quadratic formula or anything. We put, again, the products are the base and the hydronium ion concentration. So we have those here. The reactant is the BH plus. So we have that down here. We have Ka that we're using. Our pKa was 9.8. So minus 9.8 raised 10 to that power. And we end up with Ka. And so we solve for the concentration of B, which is X, which is 5.3 times 10 to the minus 11. So almost nothing. It didn't come back very much at all. We pushed it all the way to the right using acid, and very little of it came back. So let's do a top hat and we'll be done. Okay. Let's see. I try to emphasize some of the concepts that I want you to have locked in with the top hat questions. And so I want you to really focus on the concept of what's protonated and what's ionized, okay? So here, a weak base is protonated at blank pH. So think about the pH scale, think about protonation and so on. So a weak base is protonated at blank pH, low or high. A couple of people. We're running out of time, so let's go. All right, so this is how y'all answered. Okay, pretty even split. It's low. So think about low pH. That's acidic. So there are lots of protons available. So low pH, you have lots of protons available. So boom, it's going to hit that base and get stuck. Okay. So now let's think about ionized. We're looking at the ionized species, the thing that's charged. A weak base is ionized at blank pH, low or high. And then one more, and we'll be done. Okay, so that's still pretty even split. Again, bases, we're assuming they're neutral. They take on that proton, now they're charged. So that means they're ionized. It's an ion. Okay, what about acids? Okay, a weak acid is ionized, so we're talking about ionized, weak acid. So we're talking about a carboxylic acid group is ionized at lower high pH. Make your choice. Okay, very good. Come on, folks. Let's see what you did here. Yay, okay, very good. So the acids with the high pH, you're going to deprotonate that acid. It's going to be an A minus. It's going to be an acid minus, an anion. So I'm really happy that y'all got that one right. So it's just opposite for bases. Bases are protonated and ionized at low pH. Acids are deprotonated and ionized at high pH. All right. Y'all have a great day.
Oh.
Yeah. Somebody's guts. Yeah. So we're out of time, so we're going to have to